Hello everyone, and welcome to today's Plants and Python lesson. Before we get started, let's import some of the packages that we're going to need for today's lesson. So let me do that. Okay, so today we're going to talk about modeling linear data. And so in science, we often want to answer general questions using a specific sample of data. For example, say we want to know something about how the last frost date impacts tart cherry yield in Michigan. Say we had 20 years of historical data from different orchards. This is a sample, this is our sample data. So a good sample is representative of the universe of possible data points, but it's still only a subset. So if we want to predict cherry yield given a specific last frost date, for example, say May 15th, we could look at the historical data for that year, for any year in which May 15th was the last frost date. But what if May 15th was never the last frost date in our data set? So maybe some years had May 14th and some years May 16th, but it never happened to be exactly May 15th. Or maybe there is a day in the historical data that has May 15th as the last frost date, but there are other things that happened that year. So, for example, maybe there was a windstorm or a hailstorm that affected yield, or maybe there was a really sunny spring that increased yield. And so what we really want to know is the general relationship between last frost date and yield, and then we can use that information to make an inference about how last frost date was going to affect yield in a particular year. And so we can do this by making a model that describes the relationships between variables in our sample. In this case, the relationship between last frost date and the relationship between last frost date and yield. And so today we're going to learn how to do that. We're going to model linear relationships. So if you recall from algebra, the formula of a straight line is y equals mx plus b. But let's break that down a little. What does this really mean? So we can refer to y variable as the dependent variable and the x variable as an explanatory variable. So in the equation of a line, the variable y can be determined for any particular value of variable x using the values of the two coefficients, m and b. So given any x value and those two coefficients, we can predict what the value of y should be. And so what we're going to do today is make some models, and we're going to fit them, which is also sometimes called learning a model, to data. And what we're doing when we're fitting a model is estimating the values of those coefficients, which are also sometimes referred to as weights, using our sample data. So to go back to our example about cherries, we are going to estimate the value of our coefficients that we're going to use to predict yield, our y variable, using last frost date, our x variable, based on the sample of historical data from 20 years from 3 orchards. And then we can use that model to make inferences about other similar orchards in the state of Michigan. So let's start our exercise in modeling by representing that equation, the all-important linear equation of y equals mx plus b, using a Python function. So we'll start here by defining a function. So if you remember how to define a function, we're going to use the keyword def. And we'll give our function a name. Let's call it myLine. And then it's going to take 3 parameters, x and b and m. And what is this function going to return? Well, it's going to return y, which is just, so return y, which is m times x plus b. So here we have the equation of a line. So we'll define this function. And so now that we have the equation of a line translated into a Python function, we can use it to generate y values for points on any given line. So for example, we can use a line that has a slope of 0.5 and a y-intercept of 2. We could have picked any values. Those are just the values that I'm picking today. So first, we start by generating the x values for points on this line. And so for this example, let's use all the integer x values between 0 and 100. And we want to store those into a Python list. And so there are a couple ways to do that. And one way, we can use the built-in range function. So range is a function. It's built into Python. And what it does is it returns values between a start value, which by default is 0, and a stop value, excluding the stop value. And it goes by a step value, and by default that's 1 each time. So if we want to have a range of 0 and 100, all the integers there, we start at 0 and we go to 101 actually, because we want to include 100 in our sample. And we step by 1 so that we get every integer value. So let's do that. Let's create a list using the range function. So we'll try printing this out so we can see what the result is. And we'll have, so print, and then I make a list. We can use those blocky brackets in Python, mean a list. And then inside of our list, we'll have the output of this range function. So range, and then we just give it 101, which this is saying go from 0 by default to 101, but excluding the end value, by 1 by default. So, okay, so let's try this. What happens when we run this function? And you can see this isn't exactly what we wanted. We have, the output says range 0, 101. But really, we want a list that, 0, 1, 2, etc., all the way to 100. And so this didn't quite work right. So what went wrong? And so actually, this did give us what you wanted, but when you run the range function, it returns a compact form of the sequence. It tells you the start value and the end value in this special range object. And so what we really want is a list. And so to get that list, we have a couple of options. And so the first option is we can use the list function, which takes something as input and converts it to a list. Or we can use this expansion operator. That's just the little star symbol inside of those brackets, which again mean a list. And so if we use the expansion operator, we can expand the range object to make that list starting at 0, 1, 2, etc. And so let's try it both ways. So first we've got option 1, which we're going to use this list function to convert the range object into a list. And we've got option 2, which we're going to use this star, which is the expansion operator, to expand this range and make a list. And so if we do that, and then for today, right now, we're going to use option 1 here. So we'll define our x values, and let's just use option 1 since it's easy. We'll use the list function and then range 101. And so let's see what the output of these are. So if you see option 1, using the list function, we get a list 0, 1, 2, etc., all the way to 100. And option 2, we get exactly the same thing, except that we just did it a different way. Okay, so now that we have x values, we can use our function that we defined for the line to generate the y values for every x value in our list. And so again, there are a couple ways to do this. And the way that might be familiar to you is to use a for loop. And so let's look at what that would do. So if we start to make a for loop, the first thing we'll do is we'll set up an empty list to store the y values. Or empty list, let's call it y vals, and it's just an empty list, so we can use the blocky brackets here. So now we need to loop through every x value and then calculate what the y value should be and add that to this y value list. So let's do that. So for x in x vals, so that's our list of x values that we just created a minute ago, y is going to equal the output of our function that we wrote. So my line was the function, and the x will be x value. And we said that for this example, we'll set our b, which is the intercept, to 2, and the slope, which is m, to 0.5. So now we're going to calculate the y value for any given x value, and then we can add that to our list. So y vals, and then we'll append this new y value to our list. Okay, so let's run that, and actually we'll print out the results here. So if we print our y vals, you can see that we've now generated for every x value in the list the appropriate y value. Okay, so success, right? But although this works, it took quite a bit of code to write. And as you can imagine, you get even more complicated stuff that you're doing to make your list. It can get kind of out of hand, and it's a lot of work. And so there's actually a better way of creating a list in a for loop that you can actually write in a single line. And it's what's known as list comprehension. So in addition to saving space and improving the readability of your code, because when you look back through it, it's only a single line, list comprehensions are actually slightly faster at creating a list than appending each element sequentially using a for loop. It's not a big difference, but sometimes it can make a difference if you have a loop that's takes a long time to run. And so let's see how we would do the same thing that we just did in a for loop, but using a list comprehension. And so this is going to be our list comprehension, and we'll start by giving the list a name. So we'll call it y vals again, and then we use the assignment operator, and we'll assign that to this list comprehension. So we'll start with the blocky brackets, which represent a list, and then we're going to write the for loop that creates the list in one line. So we'll start with the thing that we're going to do to get each value in the list. So in this case, we're going to run our function myLine. Again, x is just x. M is the slope, which we said was going to be 0.5, and b is equal to 2. Okay, so we've got myLine x, m, b, and we need to run this function for every x value in the x values list. So we'll just write it like that, for x in x vals. And so this is a list comprehension, and it's going to do the same thing that we did before in that previous cell. And so the way this works is we've got first what we're doing to generate each value, and then telling it what to loop through. So my line x for x in x vals. So let's run that. Now we've generated both x and y values for points on a line. Let's visualize the data, and we can use the pyplot module from matplotlib to do that. Okay, so time to visualize our data. So we'll start by making a scatter plot of the x and y values. So let's plot dot scatter, and the x will be just our x values, and y is our y values. And let's just change the size of the points so that it's a little more readable. And we'll make our points black so they stand out. Okay, so let's just run this really quickly. Oh, look, we've got a bunch of points, and you can see that these points form a line, which shouldn't be too surprising. And so let's actually plot a line through those points. So we can do that using the plot dot plot. Instead of a scatter plot, we're going to make a line connecting all the points. So again, we'll give it the x values and the y values. And let's just make our line yellow so that it stands out against the black. So we'll call it yellow for the color. And so we can run that, and let's just label our axes to make this nice. So plot.y label is a function to create a y label, and so let's just call our y-axis y, and we'll make it big. So size equals 16. And let's label the x-axis as well. So plot.x label is the equivalent function, but for the x-axis, we'll just label that as x. And again, let's make it big so that we can read it. So size equals 16. Okay, so now we've got x and y, and you can see that we've got this yellow line over all the black points, and we've made a line. Okay, so what you can see from that graph is that the points fall perfectly on the line, and that's because we generated them using the equation for a line, so that makes sense. But in the real world, you never have perfect data, and so we can rewrite our equation for a line to represent what we might actually see if we took a sample from true linear data. So instead of the y equals mx plus b, we can rewrite the equation, and we're going to use slightly different symbols just because those are more commonly used in statistics than the m and b, which are used in algebra. So we'll call all our coefficients beta, and then they'll have subscripts. So the first coefficient will be beta sub 0, and the second coefficient will be beta sub 1. And that's all we're going to deal with today, but in the future you could have an equation that has a lot of different parameters, and those could be beta 2, etc. And so the equation will become y is equal to beta 0 plus beta 1 x. So that's equivalent to the mx plus b, just a different form. But then we're going to add this term epsilon, which represents error. And so that's the noise that we're going to see in the real world. What we're going to do to represent this in Python is we'll generate some random noise and add it to our y value so that we get y values that are more realistic to what actually you would see in the real world. And so let's try to define this function. We'll again use the keyword def, And then let's just call it, instead of my line, this is linear data. So we're making linear data, or we're trying to simulate linear data. So again, we're just going to take x and then the two coefficients, so beta 0, which again is equivalent to b, or the intercept from the previous equation, and beta 1, which is equivalent to m, or the slope. Okay, so let's first thing we need to do within this function is generate some random noise. So noise, and we're going to use the package numpy to do this. And so what we're going to do is select values from our random uniform distribution between, say, -10 and 10, and we're going to select a random value and then add it to our equation. So the noise will be NP, or for numpy, and then we'll use the random module from numpy, and we're going to use a uniform distribution because we're just creating random noise. It doesn't have any particular, it's not directional in any way. So the noise is coming from a random uniform distribution, and that noise values will be between -10, so that's the lower bound, and 10 will be the upper bound. And we're only going to pick one noise value. So we're going to take a sample from, or generate a random number from the uniform distribution between -10 and 10, and we're only going to generate one of them. And so that's what this line is going to do. And now let's rewrite our equation. So y equals, in this case, beta 0 plus beta 1 times x plus this noise value. Okay, and so we're just going to return y, but we're going to cast it as a floating point number, just to make sure that it is formatted correctly. Okay, so we're going to have a floating point number, which is just a number with decimal points after it, which for y. Okay, so now we've made this new function, and I have made a mistake here because I forgot to put in the colon. So there we go. We will fix it. All right, so now we have our function, and so we can use this to generate some y values. But before we do, because this equation has that random aspect to it, so we're generating random noise, every time we use the equation, we're going to get a different value for that noise because it's generating a random number. So that means if I run it and then you run it later, you'll get a different value than me. And the way that computers actually generate random numbers aren't truly random. They take an input value and then make a whole bunch of complicated calculations to generate a pseudo-random number. And it gets that input value from all sorts of things, like the current date and time, how many times you click the mouse, etc. But we can actually set the input value, and if we all set the same input value, then every time you run this cell, if you run it 50 times, you're going to get the same result every time. And so to do that, we're going to do something called setting the random seed. So we can just random dot seed, and we can give it any number, say 21, but it could be anything. And that way, every time I run this cell, we'll get the same value. Okay, so now we can generate some y values that have noise added to them. So let's call these yval2. And we'll use a list comprehension again. So we make a list, and it's my linear data, and x will again equal x, and we have beta 0 we said was 2, and beta 1 is 0.5 for x in the x values, which is x vowels. Okay, so now we've generated our new data. Let's plot this data and see what it looks like. So what we can do is make a scatter plot of the x and y data. So we'll plot the new x and y data. So a scatter plot, plot.scatter, and the x val x is going to equal x vowels again, and y this time will give it these new y values that have noise added to it. So y val 2 is the y val 2. And again, let's just make them a little bit smaller so that we can see all the points and color them black. Okay, so we've got a bunch of points. Let's plot the original line through those points. So if we plot, we have the same x values, and we have the original y values, and we'll just make it blue because blue is pretty. Okay, so now we've got a line going through the points that was the original line. You can see that they are randomly distributed around the line, and between 10 below the line and 10 above the line. So let's just label the axes again. So the y label is y. Y label y. Again, let's make that nice and big. And then the x label will look similar. Just call it x. And again, let's make it big. Okay, so now we've got a nice plot, and you can see we've got a line going through, and the points don't fall exactly on the line anymore because we've added this random noise. And this looks a lot more like data you might collect in the real world. We can see that the line still describes the general relationship between the variables x and y. And that's sort of obvious in this case because we define the general relationship and we just added noise to that. But when we collect real world data, we don't actually know what the true relationship is between variables in the whole population. But what we can do is fit a model using the sample data and estimate the true relationship. And so there's several ways to fit a model, but one way involves just sort of doing it iteratively. So you're going to take the coefficients and iteratively adjust them. So you have some start value until we've achieved the best fit model. So really the question is, how do we know which values are best? And so to do this, we need a method that will tell us how good of a fit our model has. And one way is to calculate the difference between every y value in our sample and the corresponding predicted x value. And so that's called the corresponding predicted y value. So we have the actual y value, and we have the y value that it would have been based on the equation. So that's this error of the observed is predicted is called the residual. And so what we can do is define a function that the function will do is minimize or sum up all of the error, and then we can try to minimize this function. So the function that sums up all of the residuals is called a loss function. And so if we make the loss function as small, the output of that loss function as small as possible, then that's going to be the best fit model because it's the least overall error. And so there are a lot of different kinds of loss functions, but today we're going to talk about something called L2 loss. And so what is L2 loss? It's where you take for each y value, so it's the sum of all of these values for the whole sample, but for every y value, you'll take the observed y value minus the predicted y value, and you'll square that. And then you just sum those all up. And the reason that we square it is so that you never have negative values, because the residual, the observed could be above the predicted or below the predicted, and so some of the values will be negative. But if we square the difference, then we're squaring the residual, then that's going to be always a positive number. So let's define an L2 loss function. So again, we'll use the keyword def, and then L2 loss is going to be the y observed, and we're going to need the y predicted. So, and it's just going to be the sum, so sum of every observed, so the sum, and we're going to use I here as a placeholder variable. So here, let me use some parentheses. So we're going to have I 0, and I'll explain what I is. I is just a placeholder, but it's going to have two values in it, the observed and the predicted. So the 0th value of I will be the observed, and the first value of I will be predicted. So I1, and now go outside the parentheses, and we're going to square that. And we're using a list comprehension here. So I've made this is what we're going to do to generate each value. We're going to take the 0th value of I minus the first value of I and square it for every I in, and what we'll do is we're going to make a sort of a combined object that includes both the observed and the predicted. And so what we can do is use this handy function zip, and we'll give it the y observed value and the y predicted. And so now every time we get every ith value in this zipped object, we'll have both an observed value and a predicted value. And so the observed value will be the 0th element, so and the y predicted will be the first element. So we have two elements in every instance of this zipped object. And so let's define this function. So we'll run this. And so now we can use this function to compare models using different coefficients. So we can try two models, say one using the original coefficients, and then we can modify them. So the original coefficients were 0.5 and 2, and then the modified coefficients are 0.6 and 1.8. So just for example. So let's try that. And so let's say our first y predicted values, so y predicted 1 is going to be, make a list of that. So again, we'll use the my line function, so we're just going to generate values for y values for a line using the first set of coefficients. So x, again, is just x. M is 0.5 for the first one, and b is 2. Again, for every x value, or x in x vals, which is our list of x values. Okay, so this is our first set. This is just the same as we had before. And then we have these new y values that we're going to generate with different coefficients. So my line, where x is x, but this time we'll make m 0.6 and b equal to 1.8, again for x in the x values. And now let's calculate the L2 loss for these two lines fitted through that random data that we generated. So we'll start with the first one. So the L2 for y1, L2 for y1 is going to be, we'll use that L2 loss function that we just wrote, and the observed values are these y value 2 that we generated with the random noise, and then the predicted are predicted using this first equation, so the y predicted 1. And we can calculate the L2 loss for the second predicted y, so y2 as well, equals L2 loss. We have y value 2 and y predicted 2. And so if we run this and then print out the two losses, oops, I have made a mistake somewhere. Let's check that out. So, we need the assignment operator. Missed those. There we go. Okay. So, we can see that the L2 loss for the first model is 2,991. And the L2 loss for the second model is 5,472. Hey, so it's lower for the first model. And that we can sort of intuit that if we plot these both on a graph. So let's make a plot. And again, so plot dot scatter, and the x is going to be the x values, and then we have y predicted 1. Let's just call that is going to be labeled as model 1. So that's the original model. And now we can also, oops, that's a line, so we're going to plot that as a line. And we'll first, let's make a scatter plot using the actual data. So scatter, we can have x vals and y val 2. Make those small again so we can see them, color them black here. So now we're gonna make a scatter plot of the data, the observed data that we generated, and then we're going to have plot a line representing model 1 on the graph, and then we'll also plot a line representing model 2. So again, x vals, and then y predicted 2, and we'll label that as model 2. So now we can plot the legend legend, and let's just label the axes. So plot.y label is y, and again, let's make that big, 16, and we can plot a label for the x-axis. X label and bx, and then again, let's just make our labels nice and big. Okay, so you can see now we have these points which represent the observed values, and then we've got model 1 and model 2. And you can see that model 1 seems to go through the middle of the data better, and that's why it has a lower a loss function. And so now that we can evaluate the performance of any given set of coefficients, we can try to optimize those coefficients to achieve the best fit line. And so what we're going to do is we're going to start to do that using a Python function from the SciPy package, which is called curveFit. And we will use a process to do this called least squares regression, so which is going to use that L2 loss function. And we're going to try to determine the optimal coefficients. And it's going to use an iterative method to do that. So curveFit's going to take 3 parameters. It's going to take a function to fit, and it's going to take numpy array as opposed to a list. It's similar but slightly different data structure. So a numpy array of sample X data, and then a numpy array of sample Y data. So let's start by formatting our data, because remember we've got lists of our X and Y data, so let's turn those into numpy arrays. So we've got X data, and that will be an NP array, a numpy array of the X values. And now the Y data is going to be a numpy array of those generated observed Y values that we have. So, okay, so now we've fitted the model, so now we're going to use curveFit. So we have, it's going to output these parameters, so we'll save that to this variable popt, and then some covariance parameters, which we're not going to really use, but we'll just store them in this variable pcov for covariance. Okay, so now we're going to use this curveFit function, which comes from the optimize package within SciPy. So optimize, which we imported earlier. So optimize.curveFit, and we'll give it an equation to use. So we're going to use the equation of a line, so my line, and we'll give it the X data, and we'll give it the Y data. Okay, and now once we've done that, we can calculate the fitted Y values using the coefficients generated by curveFit. And so our fitted Y values, Y fit, is going to be just the output of this myLine function using the X data and all of the coefficients. And so as we talked a little bit about before, we have in Python something called the expansion operator, which is a little star. So if we just expand popt using that little star, then we can, it will provide all of the coefficients. So we can use our function for the line, and then give it the X data, and we'll give it all of the coefficients, and that should generate the fitted Y values. Okay, so now we can calculate the L2 loss for this curveFit solution. And so the curve fit loss is this L2 loss function. And then the observed values are just those ones we generated, y val 2, and the predicted are the fitted y values. And so let's print this out in a nice way. So we'll print, we'll say L2 loss using curve fit is, and then I'm just using a placeholder here. So in these curly brackets, 0 is just a placeholder, and then we'll use the dot format function to format this curve fit loss value. Okay, so if we run that, it'll say that the L2 loss using curve fit is 2,950. And so this is our lowest loss value. So that seems like it worked really well. But I'll just give one side note is that curve fit function uses something called nonlinear least squares to find the optimal coefficients, and it uses nonlinear least squares is sort of a heuristic method, and it uses an iterative process to find them. And it's more general than linear least squares, and it can be used to fit a wide array of nonlinear models. However, we're using a linear model, and because of that, there's actually an exact mathematical solution using matrix algebra, and we can implement that in Python using a different function. So for example, we can use this least squares function from the linear algebra package from NumPy, and it's a little less user-friendly than curve fit, and it won't work for nonlinear equations, but it is probably the more appropriate solution. So I'll show you what that looks like now, and that should also help get a little bit of the math behind doing least squares. And so we need to provide our data to this linear algebra least squares function in matrix form. And so we're going to make matrix A, and we're going to use this handy function vstack, which is going to help us get that into the right matrix form. And so this is going to be some of the input data, and so we'll give it the x data, and then our matrix is going to need to have basically a column of ones in it, and so we can use this helpful np1s, which will make just a column of ones. And we can do that for the length of x data. So we're converting our x data into the appropriate matrix form, and we're going to have to transpose that, and then we'll have our alpha value is going to be the output of this linear algebra least squares function. So we use np.linalg, and then we'll use the least squares function, and we'll give it this x data matrix that we made, and then we'll give it a vector of the y data, and we'll set this parameter to none, equals none. And so you can see this is like a little bit more complicated looking than the curve fit, and it probably has some parameters that you may not be familiar with, and that's okay. We're not going to go into detail about all the math behind this. If you're familiar with how to calculate these squares using matrix algebra, this actually might make a little more sense to you. And it is the more correct solution for a linear model because it's an exact solution, whereas curve fit is the more general solution, and it uses a heuristic approach, and it iteratively tries coefficients to find the optimal ones. So let's just call this our fitted values 2, so we can compare them. So we have my line, and we'll give it the x data, and then we're going to, m is going to be alpha 0 and the 0th element of that, and b is going to be so the coefficients are stored in this 0th element of this alpha object that the least squares function returns, and this intercept will be the first element. So alpha blocky bracket 0, blocky bracket 1. Okay, so we can run this, and now we can calculate the loss function using this linear least squares. So linear least squares loss. Again, let's just use our L2 loss function. Our observed values haven't changed, y-val 2, and now we have these new fitted y values using this function. And so we'll calculate that loss, and let's calculate the difference in loss between the curve fit function, the linear least squares function. So this will be the difference between the curve fit loss and the linear least squares loss. And so we have curve fit loss, and we have minus linear least squares loss. And then we can just print out. So I just wrote this out ahead of time. So we're going to print L2 loss using the linear least squares method and we'll put in the linear least squares loss, and then we'll print out the difference between the curve fit loss and the linear least squares loss is going to be this difference. So and oops, I try that again. Okay, so now we have this linear least squares loss, so it's 2,950.087 07673 1004. So when you compare that to the curve fit, see that the difference between the curve fit loss and the linear least squares loss is 1.3642420526593924 times e to the minus 12 times 10 to the minus 12. So this is a tiny, tiny number. So technically, the linear least squares is a smaller loss value, so it is a better fit. But in all practical purposes, it didn't actually really make much of any difference. So the linear least squares gives you the exact solution, but curve fit essentially found the same solution, at least in this case. The difference is so tiny that it's probably not meaningful to us. So that's just something to keep in mind. And so in practical terms, it doesn't really make a difference. And so up until now, we've been evaluating the model performance using loss. And so another way to evaluate the fit of a model is by comparing the predicted and y values sort of directly. And what we can use to do that is a metric called Pearsons correlation. And so conceptually, this Pearsons correlation, or R, can have any value between -1 and 1. So a value of 1 would indicate a perfect positive linear correlation between two variables. So if y increased by a factor of 10, y1 increased by a factor of 10, then y2 would also increase by a factor of 10. And if they were -1, that would indicate perfect negative correlation. So if y1 increased by a factor of 10, then y2 would decrease by a factor of 10. And R of 0 indicates no correlation. And then, of course, you can have anything in between. We can compare the predicted y value from our model with the actual y value using Pearson's correlation coefficient, and that will give us a sense of how well they performed. We'd expect them to be closely correlated, and that would mean that the model performed well, and if they weren't correlated, then the model doesn't perform very well. So let's calculate the Pearson's correlation. So the model results for Pearson, and we'll use the function from the stats package for Pearson R. So it's just stats.Pearson R. We'll give it the fitted values and value 2. And then we'll just print out the results. So the Pearson R is 0.94, and then it will calculate a p-value for us, which is a very tiny number. So this is significantly correlated. And 0.94 is pretty close to 1, so we have very strong linear correlation. So we see like the R of 0.94 is very good. And when looking at fit of models, we actually often use a metric called R squared instead of just R. And so for a linear model, where we included the intercept in the model, the R squared value is simply just the square of the Pearson's correlation coefficient. So for our model, R squared would just be 0.9410, which was our rounded Pearson R squared. So let's calculate that. So R squared, the model results Pearson. So that's going to be the 0th element is actually R, the correlation coefficient. And we can square that. And then let's just print that out. So see R squared of 0.89. So this is a pretty good fit. So hopefully that was a helpful introduction to linear models. And in the in-class activity, you're going to get to apply what you've learned to hopefully an interesting problem that relates to some data collected about photosynthesis. And so I look forward to seeing you in class.